The Messerschmitt Me 262 is one of the most iconic aircraft of the Second World War. Designed and built in Germany, it was the world's first jet fighter to be mass-produced and deployed in combat. In this video, we focus on the Me 262 A1 variant, known as Schwalbe. In German, Schwalbe means swallow, a name that reflected its original purpose: speed, agility, and a complete break from the piston engine era. Because Me 262 production was heavily decentralized to protect factories from Allied bombing, many small details from structural fittings to instrument panel layouts varied from aircraft to aircraft. For this analysis, we have selected the configurations that best represent the standard Me 262 A1A, allowing us to examine the aircraft. My name is Marcus Reed, and this is Iron Blueprint. The Me 262 was a low-wing, twin-engine monoplane designed around speed, simplicity, and survivability under industrial stress. Its fuselage was 34 feet 9 inches long, or 10.6 meters. And in cross-section, it formed a slightly inflated triangular shape with rounded corners. This was not an aesthetic decision. German engineers chose this geometry because it could be built quickly, assembled with less precision, and maintained under poor conditions while still producing low aerodynamic drag. It was a shape that tolerated error, and by 1943, error tolerance mattered more than elegance. The fuselage was constructed from a combination of steel and aluminum alloys. As the war progressed, high-quality light alloys became increasingly difficult to source, so steel was often substituted where weight penalties could be accepted. The result was a heavier in several non-stressed areas, including fuel tank covers and interior panels. Structurally, the airframe was built around longerons and stringers connected by formers. These formers were made from U-shaped and J-shaped metal sheets and held in place by the longerons. The Me 262 was not only a jet fighter, it was a product of desperation engineering. At the nose, the aircraft retained a form familiar to piston engine fighters of the era. A small window was a reminder that despite its revolutionary propulsion, the Me 262 was still expected to fight in a very traditional war. After assembly, the fuselage skin was polished and painted. Gaps and seams were filled or covered with doped fabric to reduce drag. Every effort was made to preserve speed, because speed was the one advantage the system could still reliably produce. The airframe of the Me 262 tells a quiet story. This was not the body of a perfect machine. It was the body of a machine designed to survive Inside the Me 262, the fuselage was divided into multiple. These were not added for comfort or convenience. They were added because the aircraft carried fuel. A reinforced bulkhead was placed between the forward fuel tank and the ammunition storage for the nose-mounted cannons. This section was fireproofed and strengthened because engineers understood that a single ignition here would mean instant. This was not theoretical. It was based on combat experience from earlier fighters that burned too easily when hit. Another bulkhead separated the forward fuel tank from the cockpit. Behind the pilot, additional bulkheads divided the rear fuel tank. A smaller bulkhead also isolated the gun camera compartment in the nose. Most of these bulkheads were made from aluminum alloy sheets, reinforced with stiffened. The structure looked simple, almost crude, but it served a clear purpose. It allowed systems to pass through while still preserving separation. This was early risk management, built into metal. The outer skin of the aircraft was formed from duralumin. Only the area around the gun barrels was covered with steel plating, strong enough to absorb repeated blast pressure from the cannons. once assembled, but the real function of the bulkheads was invisible from the outside. They were the aircraft's internal firewall system, dividing danger. The Me-262 did not rely on one strong structure. It relied on many weak ones, carefully arranged. That was how engineers tried to keep a revolutionary machine alive in a collapsing. The wings of the Me-262 were built entirely. A steel main spar carried the primary load, while a secondary duralumin spar. These spars were connected by a network of main and auxiliary ribs, forming a structure strong enough to support jet engines, while the wingspan measured 41 feet 4 inches, or 12.6 meters. And the leading edge was swept. This sweep was not chosen for appearance. It was chosen because German engineers were already encountering compressibility effects as speeds approached the limits of propeller-driven. The Me-262 was designed for a flight regime that no pilot had yet mastered. The wings were mounted with a slight upward angle of 5 degrees, improving stability at high speed and helping control the aircraft during landing. Along the leading edge, automatic 3-section slotted slats were installed, except in the areas. These slats extended automatically at low speeds and high angles of attack, improving lift when the aircraft was most vulnerable. On the trailing edge, 2 section flaps increased the effective wing area during takeoff and landing. To reduce the risk of pilot error, the flaps could only be deployed when the landing gear was lowered. This was an early example of engineering logic replacing human judgment in critical moments. The ailerons, which controlled roll, were split into 2 separate sections on each wing. This reduced the effects of wing flexing at high speeds and preserved control when aerodynamic force. The skin of the wings was made from duralumin sheets between 2 and 2.1 millimeters thick. On the lower surface, sections of thin steel sheet were added to protect the structure from debris and engine exhaust. Every material choice reflected compromise. Speed, strength. The wings of the Me-262 were not just lifting surfaces. They were a bridge into a new aerodynamic world, built before anyone truly understood the rules of that world. The tail of the Me-262 was designed to provide stability at high speeds. Even small control errors could grow rapidly, and the aircraft needed strong aerodynamic. The vertical stabilizer was swept back at 45 degrees and carried a large rudder to control yaw. The horizontal stabilizer, swept at 23 degrees, supported 2 elevators that controlled pitch. Together, these surfaces formed a tail assembly optimized for stability rather than agility. All components of the tail were built from metal, following the same structural philosophy as the wings. Strength, durability, and simplicity were prioritized over weight savings because the swept design of the tail also reflected a growing understanding that traditional straight tail surfaces. German engineers were building for speeds that most pilots had never experienced, and they were doing so with limited data and no proven models to. The tail section of the Me-262 was not an afterthought. It was a response to an unknown future, shaped by caution rather than confidence. The Me-262 used a tricycle landing gear arrangement. This configuration was advanced for its time and provided better ground visibility and each landing gear strut was equipped with an oil pneumatic shock absorber, allowing the aircraft to handle the high weight and landing speeds created by jet propulsion. The system was operated hydraulically, extending and retracting the wheels after takeoff and before landing. On paper, the landing gear was strong enough. In practice, it revealed one of the greatest weaknesses of early jet aircraft. The Me-262 required long. While airborne, the aircraft was almost untouchable. On the ground, it was vulnerable. Allied pilots quickly learned that the safest moment, the landing gear, designed to support a new... This was not a flaw in the mechanism itself. It was a flaw in the environment that surrounded it. Powering the Me-262 were these engines represented a technological leap. They were the first successful axial flow turbojet engines to reach operational service, and they became the foundation for every modern jet engine that followed. Air entered through the open intake at the front of each nacelle and was compressed by an 8-stage axial. The compressed air was then directed into 6 separate combustion chambers, where fuel was injected and ignited. The resulting hot gases drove the turbine, which in turn powered the compressor, before exiting through the exhaust. A movable inner cone inside the nozzle controlled exhaust flow. German engineers called it. This simple mechanism allowed the engine to maintain efficiency across different power settings, a critical requirement for flight control in the early jet age. Each Jumo 004 was 12 feet 8 inches long, 81 centimeters in diameter, and weighed roughly 709. It was compact, powerful, and revolutionary. It was also fragile. Because of severe shortages of high-temperature alloys, the engines were built using lower-quality materials that could not withstand prolonged heat stress. As a result, engine life was measured in tens of hours rather than hundreds. The engines were started using a small 2-cylinder gasoline-powered Riedel starter motor mounted in the intake. Fuel used was J2 synthetic fuel, produced from brown coal, although the engines could run on multiple fuel types if necessary. With both engines operating, the Me-262 could reach a maximum level flight speed of 87. In a dive, it could go even faster, though pilots were warned not to exceed 900 kilometers per hour due to severe vibration. German pilots were the first to experience compressibility effects that no one fully understood. Prototypes reached speeds above 970 kilometers per hour, but control became unstable and unpredictable. Legends later claimed that Me-262 pilots broke the sound barrier during the engines gave the Me-262 unmatched performance. But they also defined its limits. This was a machine that could outrun its enemies, but not its own materials. The fuel system of the Me-206 jet propulsion delivered speed, but it demanded time, range, and balance. 2 self-sealing rubber main tanks were installed inside the fuselage, each holding approximately 900 liters of fuel. These tanks could feed either engine, and the pilot controlled fuel distribution using a selector switch. In addition to the main tanks, auxiliary tanks provided another 770 liters of fuel, increasing total capacity. When fuel levels dropped to around 250 liters, a warning light illuminated on the instrument panel. From that moment on, the pilot had to actively manage fuel balance between tanks to maintain stability. There was no automatic system to do this. The responsibility belonged entirely to the human. In theory, the maximum fuel load allowed the Me-262 to remain airborne. In reality, combat conditions reduced this significantly. Climb, acceleration, and high-speed every mission was short. Every decision had to be made quickly. And every minute in the air with the Me-262, it was never meant to stay and dominate the sky. Its fuel system defined it as a weapon of opportunity rather than a platform of control. Speed gave it freedom. Fuel took that freedom away. The primary armament of each cannon fired 30mm. The muzzle velocity was relatively low, but the explosive power of each round was enormous. A single shell carried enough explosive force to destroy a heavy bomber with just a few hits. Against Allied fighters, a single direct strike was often enough. The Mk-108 was not designed for precision at long range. It was designed to end engagements. The cannons were electrically fired from the pilot's control stick, and their reload ammunition was stored in protected boxes directly behind the guns, reducing the chance of jamming and minimizing feed failure. Large spherical mounts surrounded the gun barrels, allowing the guns to be adjusted for convergence. Typically, they were set to converge at distances between 450 and 500 meters, optimized for head-on attacks against bomber formation. A gun camera was installed in the nose and activated automatically whenever the pilot fired the weapon. In addition to the cannons, the Me-262 could carry unguided rockets mounted on wooden racks under the wings. Several types were tested, but the most effective was the R-4M rocket. These rockets could be fired from distances up to 1,000 meters, allowing the pilot to attack bombers without flying direct. Accuracy was poor, so effectiveness depended on volume. A typical Me-262 carried 24 rockets, 12 under each wing, which could be fired individually or in a single volley. The rocket trajectories closely matched the ballistic path of the Mk-108. The armament of the Me-262 was designed for one purpose: to break bomber formations in seconds. It was not built to fight long battles. It was built to end them before they began. The cockpit of the Me-262, the pilot sat surrounded by fuel, ammunition. At the front of the cockpit, a 90mm bulletproof glass panel shielded the pilot from head-on fire. Behind the seat, a 15mm steel armor plate provided protection from the rear. On later aircraft, this armor was extended upward to protect the pilot's head as well. These additions reflected hard lessons learned from combat losses earlier in the war. The canopy was divided into 3 sections, with the center section opening upward for inside. The layout followed traditional Luftwaffe design logic, but the amount jet flight demanded constant monitoring. On the left side of the cockpit were the engine throttles, trim controls, and hydraulic, pneumatic, and oxygen systems. On the right side were radio controls. Directly in front of the pilot, the instrument panel was divided into 2 clusters. Flight instruments were on the left. Engine instrument. Below the main panel was the rocket launch control panel, added later as the aircraft's role evolved. For aiming, most Me-262 pilots used the standard Luftwaffe Revi 16B reflector gun sight, which projected a simple ring and crosshair reticle. More advanced gyroscopic sights existed, but few aircraft received them before the war ended. The cockpit of the Me-262 was a transition space. It belonged neither to the piston era nor to the modern jet age. Inside it, a human pilot was asked to manage a machine that was already entering. The Me-262 began on the left wing. The pilot would climb up, lift the center section of the canopy, and lower himself into the seat. There was no padding. The pilot sat directly on his parachute. Once seated, he would strap in and begin the startup sequence. The process was strict and unforgiving. A mistake at any point could damage the engines or cause a fire. First, the pilot switched on the battery. The fuel selector valves were confirmed closed and the throttles were set to. The starter handle was pushed down to prime the Riedel starting motor. The pilot then pulled the handle and held it while pressing the tachometer button. When each engine reached 700 to 800 revolutions per minute, a deep pulsing sound followed as combustion began. The engine speed was then increased to 1800 to 2000 revolutions per minute. At this point, the starter handle and tachometer button were. The rear fuel tank supplied both engines during this phase. The pilot slowly advanced the throttles until 3000 revolutions per minute. At this point, the ignition button was released as the engines became, with the engines now running between 4000 and 6000 revolutions per minute. Steering on the ground was accomplished using the main wheel brakes. When positioned for takeoff, the pilot held the aircraft with the brakes and slowly advanced the throttles until the engine. Only then was the Me 262, starting a jet engine in 1944, was not a push-button action. It was a ritual. And every ritual carried risk. Once cleared for departure, acceleration was slow compared to piston. Directional control was maintained using wheel brakes only, since aerodynamic control surfaces were not yet effective at low speed. The control stick remained neutral as the aircraft gained speed. At approximately 125 miles per hour, the pilot gently pulled back on the stick. This raised the elevators and allowed the aircraft to lift off the runway with us. Immediately after becoming airborne, the pilot applied the brakes to stop the wheels from spinning before retracting. This prevented damage to the system at high rotational speeds. Only after the gear was fully retracted did the aircraft begin to climb. The takeoff of the Me 262 was the most dangerous moment. The aircraft was heavy, slow, and unable to maneuver. It was during these seconds that Allied fighters often struck, diving from above to destroy jets before they could reach safety. Many Me 262 seconds never made it past this phase of flight. In the air, the Me 262 was a predator. On the runway, it was a target. After takeoff, the Me 262 climbed to this gave the pilot both a tactical advantage. Once in position, electrical power to the guns and rockets was switched on, and the safety cover on the control stick was flipped. When enemy bombers came into view, the pilot would move to the side and above the formation, then begin a controlled dive. Speed was carefully managed. Too fast, and the aircraft risked structural stress or loss of control. Too slow. The pilot aimed to cut across the bomber box formation in a single high-speed pass. Through the Revi 16B gun sight, the glowing crosshair and range markings provided the only reference. Range and deflection were judged by experience, not calculation. As the distance closed from roughly 1,000 meters to 600 meters, a volley of rockets when the bomber filled the gun sight ring at around 300 meters. Short burst. The attack lasted seconds. There was no second chance in the same pass. After the dive, the Me 262 climbed back above the bombers for another attempt. If escort fighters appeared, the pilot simply accelerated and left them behind. When fuel or ammunition ran low, the pilot turned for home. The mission was never about control. It was about speed, impact, and escape. The Me 262 was almost done. Allied pilots quickly learned that chasing it in level flight, so they changed the rules of engagement. Instead of fighting the jet in the air, they waited for it on the ground. During takeoff and landing, the Me 200, its engines responded sluggishly at low power, and its this vulnerability became a target. Allied fighters began to patrol airfields used by Me 262 units, diving on jets as they lifted off. The tactic became known as rat catching. This method was brutally effective. Jets were destroyed not by superior aircraft, but by superior timing. The Allies were not defeating the Me 200. The jet represented the future of air combat. But it was trapped in the present. And in the present, Control of airfields mattered more. Approximately 1,000 of those, only about 300 ever reached operational units. Shortages of fuel, spare parts, trained pilots, and serviceable runways meant that the jet arrived too late. As an interceptor, the Me 262 proved that it could strike bombers faster than any piston fighter and disengage at will. But wars are not decided by individual weapons, they are decided by systems. And the system behind the Me 262 was already collapsing. Factories were dispersed, supply lines were broken, training programs were rushed. Every advantage the jet offered was cancelled by something the system could not support. Yet, the Me 262 did not disappear with the defeat of Germany. Its ideas survived. The underwing engine nacelle became the standard layout for modern aircraft. The axial flow turbojet became the foundation of all future jet engines. Aerodynamic solutions developed for the Me 262 influenced. Even modern airliners still carry the blueprint of this aircraft in their structure. The Me 262 lost the war, but it won the future. It proved that technology alone is not enough. A breakthrough only matters, and that is the lesson this aircraft leaves behind.